Okay, good afternoon everybody. It's nice to meet you again. There's a lot of survivors this year, so I'm happy seeing this. Do you have any questions? We have a lot of work to do today because, as you're probably aware, this is the last lecture of the semester for computer graphics, and we need to complete object collision. We did environmental collision last time, so we have all the knowledge and tools which we need to face the problem of object-object collision, and then we will cover a very broad overview of global illumination, the problem of global illumination. Be aware, of course, that what I will present you for global illumination is just the tip of a huge iceberg and a huge field of study that if you are interested, quindi l'ho sbagliato. Grazie. Also, I would like to review briefly with you an example of an exam and sketch briefly together with you how the solution should be given. So you more or less are in sync of what I will expect from you during the exam. Okay, so how you should answer questions, and etc., etc. We will basically cover together one of the sample exams with solution which is already available for download. So in case any of you who's listening to this wants to review everything, the material can be downloaded from the website. Okay, do you have questions? No questions, or some questions? Did you begin studying a little bit? Yes? Oh, okay. But no questions. Mm-hmm. Well, there are, I think, if I'm not wrong, that from the web page you can download a package, samples.zip or something like that, with 6 or 7 exercises. Of course, there is one exercise with solutions. There is one exercise for every kind of, subject. So you have one exercise about the Fung model, one exercise about collision detection, one exercise about volume rendering. Basically, what you will have at the exam is a slight variation of that kind of exercise. Of course, I cannot publish, okay, this will be the text of the exam of tomorrow. This is not possible. But what I can do is give you as much material as possible to feel like this. Did I understand this? Can I do this without copying every line? Can I apply my reasoning on it? If the answer is yes, then you might be reasonably confident that you will succeed at the exam. But more than this, I cannot do. Okay. Just be sure that you have understood all the slides where you have the pencil in the upper left corner. Okay? So if you have problems with the pencil, solve those problems first, because those are a very big candidate for the exam. Then there could be something also in theory outside the pencil. But the pencil, if you didn't understand the slide with the pencil, then you have problems. Okay? Then there is a forum. Oh, I'm sorry. I have to switch it off. These things get so complicated that, okay, how would it be? Vibration. Okay, thank you very much. This thing does everything except letting me call people. What I was saying about the exam. The forum, yes. It's quite hidden, but there is a sentence written somewhere in green. The FAQ, frequently asked questions, is on the forum. Okay? If you go on the forum attached to the page of Course Online, you will find, I think, around 30 or 35 questions made by students before you. They're always the same question. Oh, but there is a mistake on slide 35 because the coefficients is AAC instead of ABC. What should I do? That's a frequently asked question and has been put in the forum. Okay? There are many, many, many questions. How do you use this? How do you use that? It's always the same. That's why they are called frequently asked questions. So, before asking, go and read the frequently asked questions. You will find, also it's interesting because maybe if you find a question and say, Jesus, I didn't even understand the question, then that's a problem, okay? Okay, Jesus. Well, not everybody says Jesus, but somebody do. Yes, I tend to forget that we have a multicultural environment here. It's very American, Jesus, and it becomes Jeez, which is written, well, you can say Jesus, and it's J-E-S-U-S. Okay, it's common it's common swearing. But then the Americans usually make it brief, so it's Jeez. Yes, and it's written G and not J, E-E-Z. Okay, it means Jesus, but in short, because they're always in a hurry. It's true. It's true. Okay. In Russian we have blin, and some other words which is better not to say. But blin is okay, right? I can say blin. Yes, freely. Okay. Back to business, because we have a lot to do and not much time to use. I hope that you remember something about environmental collision, because I'm going to cover it rather quickly now. We now know how to check collision between a sphere against a plane and a box against a plane, right? What is the core idea? We shift the plane and check collision against the center. Okay? Because we always know the center of the sphere. And how much we shift of the same quantity of the radius of the sphere. Which causes you a conceptual problem when you're doing box sphere. Why? Because we don't have a radius on a box, so how do we solve that? How do we solve the problem that we don't have a radius in a box? We define, how is it called? You said you did study. You didn't arrive to collision. You're still at what is computer graphics? We define an efficient radius, which has a problem. What is the problem with the efficient radius? Yes? The mutual position between the natural axis of the box and the normal of the plane. So every time the box rotates somehow, it changes the position of the three axes in relation to the plane, we have to recalculate the efficient radius. The idea so this is basically sphere against plane, box against plane. idea here is to try and determine collision between two objects instead of one object and a plane, which is one object and its environment. There are two cases that we could consider. Well, basically we consider a sphere against another sphere. And the general situation is that sphere A is moving with a velocity vector, which is known, and a sphere B is also moving with another velocity vector, also known. So we are going to check if two moving spheres in 3D space are going to collide or not, at what time and under which conditions. The idea for solving this problem is to shift to relative motion. That is, keeping one of the two spheres considering it fixed and recalculating the velocity vector of the other sphere using the equation of relative motion. So in our idea, one of the two spheres will always be fixed and the other sphere will be considered as moving. In this way, we can somehow apply the same concept of the plane, which was fixed, not moving, and the sphere, which was moving in the case of environmental collision. So how do we do that? Well, there is the general case, the two objects are both moving. Then there is a lucky case, one of the two objects is idle. And what we usually will be going to do is bring the case A to case B. That is, always consider that one of the two objects is idle by using the concept of relative velocity. That is, I subtract the two velocity vectors of case A, which is the case in which both spheres are moving, and I consider one of the two objects as idle. For example, consider two spheres, radius RP and RQ, respectively, moving in our usual span time of attention, which is between T0 and T1. P1 and P2, the positions of the center of this first sphere at time T0 and at time T1. This is given in order to allow us to derive a linear velocity vector, as we did in the environmental case. In the same thing, Q1 and Q2 are the centers for the second sphere. Therefore, the velocities for the two spheres will be Vp and Vq. Those are the two linear equations of the centers of the spheres using the velocity vectors. You can, in general, found a collision equating the distance of the centers of the sphere to the sum of the two radii, like this. So when this will happen, when the square of the distance between the two radii equals to this equation over here, you have a collision. This is the theory. If you solve the preceding equation, you obtain two possible values of t. The lesser t is the time in which collision occurs when the spheres are going one nearer to the other. The second value indicates the time in which the two spheres are tangent when they start moving apart. In some cases, the denominator of the root equation is 0. That means the two spheres do not collide, either because they are both idle or because they travel in the same direction with the same velocity. To solve that equation, we can solve it analytically by making this substitution: A equals to P1 minus Q1, and B equals Vp minus Vq. And if you make that substitution, you can choose the minimum value of t by applying this formula. Once you find the time of collision, then you can find the point of contact in the usual way, by moving it along the normal for the quantity of one of the radii. In this case, actually, we didn't require, we could solve the problem theoretically by just writing this equation and solving it analytically. With the sphere is fine, you can do it. With the box, this is much harder, and we have to resort to relative velocity in the way that I described you. Why it is hard? Because there are many ways in which a box can collide against another box. Do you remember the problem of 1 feet, 2 feet, and 4 feet when we were checking collision of the box against the plane? You remember that? We've been doing drawings, and we've been looking at ways to understand if one box going down to a plane was supposed to going down on one corner or on one side or on one edge. Okay? So one corner is 1 feet down, one edge is 2 feet down, and one side is 4 feet down. So 4 points of interaction against the plane. In order to solve box-to-box, what the idea that we have is to use box-to-plane by simulating a plane, keeping one of the two boxes fixed, and considering different kind of box-to-plane with one of the box fixed. The problem is that we don't know in advance against which one of the sides of the box the other box will be colliding. So what we actually will do is to stop one of the two boxes and then perform box-to-plane for every plane of every side of the box which I kept fixed. Do you see what I mean? So in theory, what would I have to do is to check to make box plane 6 times. 1 for every of the 6 sides of the box which I'm keeping fixed. In this way, I will find if the box which is moving is going to collide in our relative motion coordinates against which of the planes to which one of the sides belong. When I find the plane, that is the side, over which there is a collision, then I can start to determine if that collision actually happens inside the boundaries of the side or outside. Because the plane is infinite, right? But the side has a definite size. Then I have to decide if it is 1 feet, 2 feet, or 4 feet down. Then I don't finish because I have to check also the other way around. That is, the box that was moving first I have to keep fixed. And the box that was fixed in the first 6 checks, I have to get it move. And see if there is a collision under which plane in the other way. This is the general idea because you don't know in advance. So you have to check one way, box A moving against box B fixed, for 6 times to search which one of the planes, that is which one of the sides, is candidate to get a collision. Then you have to get the other way around. So the box which was moving before, you keep it fixed, and the box which was fixed before, you make it move. And you do again 6 times a box plane to check if you have a possible collision. Of course, before doing all this stuff, the best thing to do is to consider the problem using bounding spheres. That is, you could determine initial radii for the box and use those radii for creating spheres, which are encapsulating, embedding the boxes, and try to make a sphere-sphere collision using this kind of check. If this kind of check is negative, that is, you don't have roots, then you may safely assume that you will not have a box-box collision. If you do not have collision between the sphere, then the boxes will not collide. End of box-box collision detection. You can use a bounding sphere by using an effective radius like this, for example. R, S, T being the vectors describing the three sides, the three axes of the box. But if sphere-sphere is positive, which means there is a possibility that the spheres, as defined as this, with this radius, collide, then you are bound to understand how the boxes actually collide. If the abounding sphere do not collide, then you can safely assume that the box within them will not collide. As you can understand, there are four possible types of box-box collision to consider. A vertex, which is a corner of one box, collides with a face of the other box, a side of the other box, or with a vertex of the other box. And then all possible permutations of this situation. A side of one box collides with a face of the other box, or with a side of the other box when the two sides of the two boxes are parallel. Well, it takes a lot of toilet sitting to visualize, but if you sit long enough, you will be able to recreate in your mind all these situations. A face of one box collides with a face of the other box, and the two faces are parallel. Okay? A side of one box collides with a side of the other box in a single point, and there are no sides parallel to the face of the other box, this is something like, well, side against side in one point. Okay? Something like this. Then you can have something like this, the corners, then you can have the faces. Okay, then you can have the side against one flat face. There are several combinations. Ideally, to make a precise box against box, you should be able to understand every possible configuration, because you want to know, if you wanted to know precisely, which is exactly the collision point, if you want to know. The first cases, 1, 2, and 3, could be handled, or these are just ideas, could be handled performing a collision test, a box against plane collision test in both directions. Box P over Q, and then box Q over P. The box against which the test is performed, whose faces are considered belonging to the plane, is kept idle, and the relative velocity is calculated by difference for the other box. So it is something you just, for example, if you want to do the relative velocity of the other one, of A against B, you subtract the velocity of B from the original velocity of A, and then you have the relative velocity of box A against B. Then you have to determine the planes related to the faces of the box you are keeping idle. Instead of using n, as normal, you will use r, s, and t. So this will be your vector defining direction of the plane. The position of the vertex will be this one. In this case, you will have to do, as I told you, 6 tests, because you have minus r plus r, minus s plus s, minus t plus t. And if you have a positive test, then you can find the position of the collision and check if the coordinates of the collision happen to fall inside the actual face of the box. Since most of the collisions belong to the cases 1 or 3, this method, which is valid for 1, 2, and 3, is okay. I mean, it's lengthy because it takes you to make 6 box planes on one side and 6 box planes on the other side. This is the worst case, okay? That you find the correct collision at the end of the 12th test. But in this way, well, it's very mechanical, it's very heavy, but it covers the most of the situation. Why? it doesn't cover all the situation, because I have one specific situation in which I cannot represent the collision as a box plane by keeping one of the two boxes fixed and imagining the side of the fixed box as a plane, which is the case in which I have a side-side collision at one point, and those sides are not parallel. So it's I would like to have two boxes to show you in 3D. Well, imagine this is a box. This is the side. This is another box. This is the other side. So when I have this kind of collision, you see, I do not have a situation in which I can, in my mind, say, I'm checking the collision of this against this plane, right? I cannot do this because I have a line and I have another line, so there is no plane in this situation. So this kind of method of keeping one box still, imagining 6 planes for each one of the sides, and checking with the moving box against each one of the 6 planes does not work for case 4. A side of one box collides with a side of another box in a single point. Because I cannot model a plane, I cannot decide a plane when I have that kind of collision. Okay? Because it's a collision occurring on one single point of 2 sides. So there is no possibility to define a plane along which calculating the collision. So this system works for all the first 3 cases. It doesn't work for the 4 cases. I have just sketched roughly an idea of what you could do to handle case 4. The only way to do it is to change the whole coordinate system of one of the 2 boxes to a new coordinate system which is orthogonal and normalized to the other box, in a way that I can create a plane to test against Q. So the idea is, okay, with this coordinate, that box is not, I cannot define a plane. But I could rotate the coordinates in a way that a plane is definable. So basically, you have to apply this one. It's already calculated for you. You rotate one of the 2 boxes using this one. You completely change the coordinate. And then you can define a plane around the sides of those boxes and perform. You have to change all the velocity vectors, of course. And then you can perform a check like in cases 1, 2, and 3. So I don't really want to go into this. My idea is that you understand the geometry of the problem and you focus actually on how you could do the first 3 cases. And in the unfortunate case that you need to implement something and you need to consider also case 4, this is an idea of where you could go. Okay. These are the 6 planes that you would be able to use after the calculation to check the collisions. So you could do 6 checks against this one. But you could do these checks only after that you recalculated all the coordinates, all the velocities, using this transformation matrix. Okay. This is basically it. I'm not going to say more about this. And okay, we go to the other subject, which is global rendering. I will explain you basically the foundational ideas of the two most used global rendering techniques, namely ray tracing and radiosity. There are several other approaches, for example, the Cook-Torrance approach. If any of you is interested in this kind of topics, you are free to, well, we can agree in any kind of research or thesis or whatever applied, well, whose goal is to get in deep, to get more involved in the ideas of global rendering. As you can understand, there is a lot to know about geometrical computation and geometrical computer graphics and rendering and illumination. So I am aware that sometimes the things that I present to you are not full solutions. And this is certainly the case for this lecture about global rendering, which is really just tasting the subject. However, when presenting topics in a course which has a limited amount of hours, one has to make choices. So what I have chosen during these 5 years was always to just give a hint of the complexity of the problem over here, and leave open discussion for those of you who are interested in doing more, either by using or either by implementing or studying a project, for example, for the Laboratory of Computer Graphics, which is 2.5 credits next semester, or with a thesis or whatever. So just to introduce you to the subject, you already know something about rendering and illumination because we have been covering rather in detail Phong illumination model. And we have stressed the fact that Phong illumination model is local. By local, meaning that if you remember how Phong works, you start from a certain number of light sources. You define for each light source its type. So whether it is, what are the possible kinds of a spot source, or, sorry? No, it was too soft. Ambient, very good. So speak up, shout like a woman who knows that she's telling truth to the world. Ambient. Or, again, the simplest one, point source. Then there was something strange, that is we had to assign, well we had and we have, to assign to the light source specific parameters which are related, actually it's a matrix. Why it's a matrix? Because colors. Which colors? RGB, so that's one side of the matrix, and on Y it's a matrix. It's actually actually a 3 by 3 matrix. Yes? Yes, that's the contribution, the emission for the surface contribution, specular contribution, the emission for the ambient contribution, and the third one was diffuse. No, that's the other one. That's the absorption, diffuse. Okay? So it's 3 by 3. You have to specify at the source level how much is the intensity for the red channel for the specular contribution. How much is the intensity for the red channel for the diffuse contribution. This is kind of crazy. It has no attached to the physical reality of the light source. Okay? It's just a convention that Phong made up in order to allow you to fiddle around with the parameters and the configuration in a way which gives you enough flexibility to search to the effect that you're really looking for. And once we had defined the light sources, when we can consider one single point on the mesh and construct on that point in which we are considering the incoming illumination, what? Do you remember? What we will calculate on the point in which you are considering illumination? A group of 4 vectors which are the vector, the normal vector against the surface, the vector which is representing perfect reflection. Absorption, no, is not a vector. The direction between the viewer and the point, and the direction between the source light and the point which I'm considering. So it's 4 vectors. Using those 4 vectors, plus a few other parameters, like, for example, the shininess of the material, if we are using a spotlight source, the orientation of the spotlight source, and so on. Then we could use attenuation coefficient for the attenuation factor, do you remember? In the end, we had such an equation, which was actually a vectorial equation, which gave an intensity on the point of the mesh in the red, in the blue, and in the green channel. Do you remember a little bit? It's a little bit hazy, I think. You should review it carefully. In all this process, never is mentioned, check if there is something else around that point in which you are calculating the 4 vectors, which might interfere with the color or with the shade of that specific point. There is no hint or no idea about that. So there is no calculating shadows, there is no calculating mutual reflections, there is no calculating occlusions between a light source and the object we are considering. Okay? What if an airplane is passing through my point and the light source? Okay? It's going to cast a shadow. But what are the rules for calculating shadow in the Phong model that we have seen? There are no such rules. Why? Because that kind of reasoning is inherently local. So it's just considering the light source, the point, it's not considering the surrounding environment. This, of course, has the benefit of being straightforward, easy to implement, easy to understand. But has the drawback of providing a result which is viable, but not realistic. Why? Because in reality we have shadows, we have mutual interference between objects and the way objects exchange color and light. We have reflection of the image of other objects on a specular object. In order, therefore, to create a rendering which is more realistic, we have to contrive, to invent more complex ways of calculating colors, calculating appearance of objects in an illumination model. A model which is not only considering the point around which I'm performing my illumination calculation, but also at every time all the surrounding environment to evaluate which are the mutual interaction between light sources and the object, and between other objects, the light sources, and so forth. These models are called global rendering models. They're called global because at every step, at every time, they consider globally the whole environment in order to calculate a realistic shading. Therefore, in a global rendering model, I will take into account, for example, the effect of occlusion shadows. Occlusion shadow is a shadow which is created because there is something between you and the light source which is shining over you. Specular reflection, so mirrors, for example. You could never represent correctly a mirror using a local rendering approach. Why? Because you need to know the shape and the configuration of another object which is right in front of the mirror in order to create the visualization of its reflection. And even if not mirror, any object which is sufficiently specular will convey at least part as an image on it, part of the objects which are surrounding it. there are two basic techniques to apply a global reasoning for the rendering. One is called ray tracing. Ray tracing is a direct application of optical geometry, and it's actually an extension of the Phong model. It tells you how to apply the Phong model not only locally on that point, but correcting, adjusting the way you apply the Phong model according to global considerations, which are modeled as information gathered, discovered through a cast ray. The idea is like this. I cast, I throw, I launch a ray from the center of projection, that is the viewer, to the scene. And I start following the reflections and the refractions that the ray is subject to because of its encounter with materials and objects within the scene. I keep following the ray until I reach so many levels of reflection, that is the depth of analysis that I want to carry, or until I reach the light source. When I reach the light source, that ray is good to carry my color computation. At every point in which I have a reflection, an intersection between one ray and one object of the scene, I perform a Phong calculation model. The result on the frame buffer of the color that I want to represent will be the result of a composition of all the Phong calculations at all intersections of that specific ray. In this way, I will be able, using the rays, to understand the mutual interaction of reflections. So how the color is changed because I have a mutual reflection of one color against another color. And this is the first method in ray tracing that is used for handling how color changes because of mutual reflections. Then you have another family of rays which are called the shadow rays. Shadow rays are cast to check occlusions. That is, to check where actually is the position of the light source and of the objects in relation to the center of projection, and to evaluate where shadows might be. You can have, well, the more complicated is the ray tracing model, the more is the family of rays that you might have. So you might cast rays to intercept or to explore geometrically other specific things. But mostly, you cast rays to model how lights interact, bouncing off and on objects in the scene, and if and where there are shadows because of occlusions between the place in which, between the place of the center of projection and the light source. One another interesting thing that we have in ray tracing is that its complete name is backward ray tracing. So ray tracing in the inverse direction, backward. Why is that? Because physically, a ray of light starts from the light source, bounces on the object, and arrives to the viewer. You have probably noticed that we do exactly the inverse. We cast the ray from the center of projection and check if we reach the light source. Why is that? That's for economy. Because if I if I start with one ray starting from the center of projection, I have no idea if that ray will arrive to the center of projection. And any ray that does not arrive to the center of projection is a ray which is not seen by the viewer. You see what I mean? So in the end, what we will actually do is to rationalize, digitalize this kind of approach by casting one ray for each subdivision of the frame buffer from the center of projection and check what we intersect. If we intersect an object, if we intersect a light source, how far we are from the light source, how far we fall from the light source. So you see, starting from the light source would be unreasonable, because it would mean, theoretically, casting an infinite number of rays in an infinite number of directions in order to find out which rays are actually going to reach the center of projection. Whereas if I move everything backwards, which is I start from the center of projection and cast from the center of projection, I already have a guarantee that I am tracing something which is arriving at the center of projection, which is what I want. Any ray that does not arrive, does not converge to the center of projection, is a ray which cannot be seen, because it doesn't enter the eye of the viewer. That's the idea of backward ray tracing. So this slide basically explains you how it works. For each ray passing through a pixel of the frame buffer, the primary ray, you intersect the ray with a list of objects in the scene and evaluate if an intersection occurs. There can be no intersection, more than one intersection, independent of how it reflects or how it refracts. If the ray intersects the surface of an object, then we have to compute the distance from the pixel which is hosting my cast ray in the viewing plane to the intersection point. The intersection between the ray and the surface are computed using the coordinate system of the object. Okay, this is something you are interested in if and when you will be writing your own ray tracing program. So these are some tips. I'm not going to delve much into this. But the main idea is that when you're casting these rays, you are building a data structure. What's a data structure? It's a way for you to organize data that you are collecting while your program is running. Okay? It could be a matrix, it could be a vector, or it could be a tree. It's interesting that it is a tree because you know that we can traverse tree very quickly when you're looking for something. So the idea is to organize this data, which is what is the illumination parameters, what are the illumination conditions at every point in which I have an intersection in the scene, organizing them in a tree, which is called the ray tree. After all the surfaces in the scene have been tested for intersection, the intersection which has the smaller intersection distance is the visible surface on the specific pixel. Subsequently, it is necessary to compute the reflected ray and the refracted ray, if applicable, starting from the intersection point. These rays are called the secondary rays. So when you cast a primary ray, you get this intersection. The color of this pixel will be determined by the first intersection, the one which occurs at the lesser distance between the frame buffer and the object. But you will know by the ray tree, that I will show you later, that the ray goes on in its life. So the color of this pixel will not be given only by this intersection, but you will have to consider all possible reflection. For example, the reflection between, for example, the fact that this cylinder somehow reflects on that point of the cube. So you will alter that color using more information deeper in the ray tree. This will make your color decision at this level much more realistic than just applying the fung model one time over here. See? You model the fact that there is some kind of reflection, so you have to add the contribution of, how to say, a new light source. Well, a new light interaction of this ray shining over here. The ray which are traced because of a reflection or because of a refraction are called secondary rays. You go on like this, looking for reflections or refractions. So you keep going on, building more secondary rays. Well, you actually could say tertiary rays, fourth order rays, fifth order rays. You go on like this. Well, for simplicity, they are called secondary rays, even if it's already the third or the fourth intersection. For how many levels? For how many levels you want. It depends from your patience. It depends from the memory capacity of your computer. It depends from the speed. But basically, you decide what is called the level of recursion. That is, how many times you want to go deeper and deeper in your recursive algorithm, or how many levels you want your ray tree deep. Of course, the deeper you go, the more accurate will be the color you're going to get, because you're taking in consideration not only the first reflection, but the reflection on the first reflection on the object. You see what I mean? Hello. And if you even go further, you can take into account the reflection on the reflection on the reflection on the object you are considering. This also builds up, contributes to generate a realistic representation. New secondary rays are reflected or refracted between objects belonging to the scene. Each time there is an intersection, this one is added to a binary tree data structure. So a data structure which is made like a tree, which always have only two branches. I will show you why. Usually the left branch is used for the secondary rays generated by reflection, and the right branch is used for refractions. So potentially you can go through a transparent cylinder. Casting a ray through a transparent cylinder means that your ray actually doubles. Part of the intensity of the ray is reflected and creates a reflection secondary ray. This reflection secondary ray will generate other reflections that will be placed in the left branch of your data structure. The refracted ray through the cylinder will create another ray which potentially can go and hit another object, other which, again, you still can have a reflection and a refraction. So the tree builds on. The maximum depth that can be reached by a ray tree is usually an input parameter set by the user or by computational constraints. Available memory, rendering performance, how many years you can wait for the result. So it depends. If you can wait 20 years, then you can go to 500 depth level. A path in the ray tree goes to the leaf node. The leaf node in a tree is when a specific path in all the branches arrives to the end. That's called the leaf. A path in the ray tree reaches the leaf when the ray does not intersect any other surface, so you have no more intersections. Or the ray intersects a light source, non-reflective, because otherwise you could, in principle, keep on reflecting from the light source. The generated branch in the tree has reached the maximum allowed limit. That is, you are at the bottom of the allowed recursive depth. This is an example You cast a ray from here. Well, this is a scene with 3 spheres on it. Sphere S1 and S2 are made of some kind of glass. Sphere S3 is completely opaque. I'm casting one ray from the center of projection in this direction, or like this, for example. Okay. So the first intersection I have is with sphere 1. Sphere 1 has the capability of reflecting my ray and of refracting my ray. So part of the energy will be reflected, part of the energy will be refracting, generating 2 secondary rays. The first secondary ray is R1, created by reflection. The second secondary ray is T1, created by refraction. How do we represent this? That the first surface I get is the surface of object S1. So S1 will be one node. Inside this node, I will typically store the coordinates of intersection. So what are the x, y, z of the intersection in which I have the generation of the refraction? And the intensity in red and green and blue obtained applying the Phong model at this point. You could also put more data if you think which is useful for the kind of rendering you want to do. But typically, at least the coordinate in which you have the intersection and the illumination value at that point. Then you have to say that from that point you have 2 rays which are generated. A reflected ray which is on the left branch, a reflected ray which is on the right branch. You do not have any other intersection from the right branch, so S1, so you don't have any other node in here. But R1, for the geometry of your scene, goes on and creates a reflection and a refraction on S2. So I have another tree, another branch. Then I have T2 in T2, which is a reflection caused by the refraction of R1 over S2. So you see, I can go on as many times I want. It depends on how many objects I have. The idea is for every cast ray, you have an associated ray tree, which gives you the sequence of objects which are involved and why. The predominant color will be given by S1. But when you will be rendering the object, so you will find out that you need to know how it is. Well, you basically will use the Phong illumination model value on S1. But then you will also apply to it some correction given by the illumination model, the value of illumination on 6.2, on X2, on S2, and the value on S3, using any kind of composition algorithm that you want. But this is the basic idea. What does it mean? It means that this method is heavily dependent on what? On the surface being ideally specular. Because I have an assumption that when I have a reflection, for example, R1, I just have one ray which is reflected from the surface. Who can do this? Only an ideal mirror. So, using ray tracing, I'm actually rendering a world of ideal mirrors, of objects which are almost perfect specular. This is why, did you ever see the result of a ray tracing image? Especially, I don't know, around 10 or 15 years ago, if you had a chance to see some synthetic generated images, that was very clear. Today is less clear because, of course, the algorithms have evolved, the approaches have been intermixed, so the effect now is much less evident. But in first ray tracing, it was very clear that the scene was artificial because everything was very shiny. You remember, everything is polished in wax. Everything very shiny, everything very reflective, very specular. So what you usually saw were crystal spheres or metal spheres or glass spheres with robots in it and very shiny ceramics floors. Okay, do you more or less know what I'm talking about? But everything, well, in general, the result that you have with such an approach, because of the nature of ray tracing, is that your resulting rendering is always very shiny, very reflective. Everything seems covered in wax. Why? Because if I would relax this limitation, and I would say this material is not so specular after all, it's diffuse, then to make it diffuse, I would be forced to generate for every reflection not just one ray, but several rays. In an ideal diffuse, in an ideally diffuse material, I have an infinite number of rays which are homogeneously scattered in all directions around the intersection point. You remember the drawing for diffuse materials in Lambert's law. But if I did that, an infinite number of rays for each possible reflection intersection at the material, my beautiful binary tree data structure would go to hell. I would have at any possible node not a binary tree, but an n-array tree, where n is the number of reflection I want to use to model the fact that I'm not specular anymore, but diffuse. Well, I can do that, but then I have to be prepared for the fact that I could have, I don't know, 5 possible branches for every node. At first level, second level, third level, and the more I go down, so deeper and deeper, the more complex my data structure becomes. In other words, the ray tree explodes. Well, it starts to get manageable at the first 2 levels, but the deeper you go, the broader it gets. So, of course, if you want to be able, remember that you have one ray tree for every possible cast ray, yeah? So, if you want to have a chance to manage all this data, then, of course, you have to perform limitation both in depth and in breadth, that is, in width. That is, in the number of scattered reflected rays that you allow. And you are forced to bring down that number, maximum of 3 or 4, which still is not much for a diffuse material. This is why the main problem with ray tracing is that you cannot handle well diffuse materials. Everything seems to be rather shiny because of this reason. Okay, this is how you compose the intensity along the path in the ray tree. You store every Phong node in every Phong value in every node, and then build on. After having completed the binary tree for the pixel, consider the current iteration. The intensity values found and stored in each node are added together, starting from the leaves of the tree. The intensity at the surface determined by each tree node is attenuated according to the distance from the originating surface of the ray. Of course, they have also take in consideration that you have to consider the other reflection, but you have also to consider that those objects are getting more and more distant. So their contribution will be less and less until it will not be very significant. The final intensity that you obtain is the sum of the attenuated intensity computed navigating from the leaves to the root node of the ray tree. If the primary ray of a pixel does not intersect any object in the scene, the ray tree is empty. Therefore, the pixel is assigned the background intensity, which you also have to declare. Okay, this is again something about refraction and reflection. We already know this. The main problem that you have, well, the interesting geometrical problem that you have in ray tracing is that you have to perform a lot of intersections. Of course, when we are dealing with how we place objects in the scene, we practically never have primitives in the scene. I've been talking about spheres. But if you're considering OpenGL, or if you're imagining doing things in OpenGL, you don't have the possibility to plot a sphere primitive. What you do instead is creating an approximation of the sphere using a technique which is called polygonal subdivision. I think you did this with Raffaella, right? So you did an algorithm that created a sphere using a depth of subdivision, so a number of polygons. The smaller the polygons, the nicer the sphere. This is the general approach. In general, we do not intersect with primitives, spheres, cylinders, cones, whatever, but we intersect with polygons. A polygon being the building block of the mesh being the hollow surface which is representing the object in my scene. So everything boils down means it's reduced to the problem of intersecting one ray with a triangle, which is hopefully the polygon we use for building my mesh in OpenGL. And this is a couple of ideas in which you can handle the problem of intersecting the ray with a triangle. If you know P0, P1, and P2, which are the vertices of the triangle, then you can calculate the normal of the triangle using the usually vector product technique and vector product convention that we already know. So he's subtracting the vectors 2 by 2 to obtain direction vectors, and calculating the vector product between the two vectors of direction that we obtain to obtain an orthogonal outgoing in the direction of the right-hand rule, which is the normal to any point of that triangle. Then I define the plane into which that triangle is laying. That is easy because I have the normal, then I pick P0 by definition, therefore the plane over which my triangle is laying is this one. Then I know how to write a ray over here. This is the representation of the ray. So I can cut with the parameter t. Then I have the ray, I have the plane. I calculate where do I have a ray plane intersection. If the scalar product between the plane and v, which is the direction of extension of the ray, is 0, then you have no intersection between the ray and the triangle because the ray and the plane are parallel. You can obtain the direction of the cast ray, for example, like this. You know that the cast ray starts from the COP and goes through a pixel. So you have to put Q in the pixel of center of projection, and choose the pixel for which you are casting the ray, and define the definition like this. So you take in the pixel that you are considering for building the right ray, the origin pixel that you are considering, and define V in this way. The value of t, that is the parameter, gives you the intersection with the plane to which the triangle belongs, which is not necessarily the triangle itself. It could intersect outside the triangle. So if you have an intersection, what you have to do is to determine if the coordinates of the intersection belong to the point. Okay. So you have understood that this kind of problem is basically a full, complete geometrical problem in which you can find recursively intersection, and at every intersection you apply the Phong model. So everything is very vector-like, everything can be solved with matrices, everything has a very neat geometric nature, completely in line with what we have seen so far. But this geometrical approach, as I told you, has the problem that it does not allow us to obtain a completely realistic effect because it's limited in breadth and in depth. Everything will be therefore dependent on the fact that we need to stick with specular surfaces. Since this was limiting and not satisfactory, another method was studied, invented, researched, which is called radiosity. The goal of radiosity is to obtain a more realistic, a more physically based effect, which allows you to properly illuminate, to properly shade diffuse materials without the limitation of the ray tracing method. The idea has been taken from thermodynamics, where radiosity is actually the rate at which heat energy is leaving on the unit of time a unit of surface. So you calculate the radiosity of a roof, or in order to check whether insulation is suitable, and to evaluate the transfer of heat between bodies. The idea, therefore, was to, since heat is actually electromagnetic energy, which is exactly what light is, the idea was to relate the concept of heat with the concept of light and color, and to use the same approach of energy balancing, which is used in thermodynamics techniques, to create a balance equation for illumination energy and therefore color. So the idea of radiosity is to create a system, a linear system of equations, which allows me to assign a quantity of energy for each unit surface in my scene. When I completely solve the system of equation, every single subdivision of every surface of the scene will have a value of energy, of light energy. When I will know this value of light energy, I will convert the level of energy into color. And the color is something that the user, the viewer, can see. So we subdivide, the idea is we subdivide all the surfaces in the scene in very small areas. The smaller, of course, the better. These small areas are called patches. Well, one patch, two patches. I create a linear system with this idea that the global balance of all energy outgoing and ingoing from all the patches of the system has to give you a net balance of 0. Okay, so all the energy has to be balanced. This works because also the surface of the light sources is taken into account. So like, for example, I have this light source. This light source has a very definite surface. So I will divide, well, it's already divided for me in patches, you see, so it's very convenient. Every patch will have a radiosity rate. That is a quantity of energy over the unit of time in the unit of surface, which is leaving the patch. All the energy per unit surface per time, which is leaving that patch, has to go somewhere. Okay? There has to be a balance of energy. Where does it go? Well, most of it goes to another patch, which is over here. Okay? Well, here also I have a patch subdivision. Okay? So, this quantity of energy is coming into this patch. Part is coming inside, part is getting back to another patch, for example, this one. Okay? So, what I have to do, as you can start to understand, is to create a system that balances the radiosity of each pair of patches. So, some is going out, some is going in, and there is something left, which goes there, and there, and there, and there. Picking everything, the sum of pluses or minuses has to get in balance, that is being 0. In this way, I know exactly which is for each patch the difference between how much energy I absorb, how much energy I give back, which gives me the level of energy of each patch, which gives me the color of each patch. Okay, this is the theory, roughly. We will go a little bit more in detail, but not much more. But just to understand, which is one thing in general, and one thing is to do it. So as you can understand, the method is rather complex, and it lays its roots in physics. Until now, we actually, almost nothing we did had to do with the real life, or had to do with physics. But with this method is very much physics. So, the result is that you can obtain, as a result, you can model lighting effects in a quite realistic way. Even, for example, in a situation like a room like this, we have a situation similar here because part of our wall is blue, and in front of it, in the corner, there is a part which is white. So if you look at what happens, you see that part of that white wall gets bluish because it's near a blue part. So you have a reflection and income of blue energy from surrounding patches. This is something that is very difficult with diffuse material like this wall to model in ray tracing. Actually, you don't see it in ray tracing. But in radiosity, what you will have is that, in fact, you have in your result the same diffuse effect in this situation that you have in reality. So you have much more realistic effect, of course, at the price of a much higher conceptual and computational complexity. So if I wanted to perform radiosity on this kind of scene, for example, you see, everything has to be divided in patches. You do not need to make patches the same everywhere. You can choose some regions of your space to have large patches and some other region to have much smaller patches. It depends on, you can do this automatically with an algorithm, for example, that according to the curvature of your object, where you have more curvature, for example, you're calculating a second derivative. When you have more curvature, then you make the patches smaller. When you have a second derivative which is flat, then you make the patches bigger. There are several approaches in literature to create automatically patches and interactions. So it's really a very deep subject, as you can imagine. There's a lot of people who have been working on it and is still working on it. And create a balance between every possible couple of patches to get the quantity of energy for each patch. Here there is a very brief discussion without the idea of giving you a full course of physics on how and why we could relate energy to light and the definition of radiant energy. In the quantic light model, radiation energy is carried by photons. In a light monochrome radiation, the energy of each photon can be expressed as E equals to hf, where f is the frequency, which determines the color of the light. For example, blue light has a high frequency and red light has a low frequency. with h, which is the Planck constant, which is independent from the frequency. So starting from here, here we have our link, the link that we're looking for. The link between energy and color, right? It is carried by the frequency, which is giving the color, through a constant, which is the constant of Planck. So it is true, and it is proven in physics, that the quantity of energy can be related to the color. And this is why the radiosity method works. The total energy of a monochrome light radiation is the sum across all photons of the E value of each photon. Why do I always referring here to a monochrome light radiation? Because I am assuming a light source which emits with only one frequency, which is hardly the case, as you probably know. Okay? Usually when light source emits, it emits on a complete range of the spectrum. So you have an integral of, you should make an integral between all the ranges of frequency over which a light source emits. Typically, when you see a white light source, this is because it emits above practically the whole visible spectrum. So it emits in red, in blue, in green, for sure, and everything in between. Radiant energy at a specific light frequency is also called spectral radiance. Light emission include, however, more than one frequency. Okay, I just said it. Okay. Sometimes I don't realize that the things that I'm saying are already written there. Okay. Then we need something which is called, do you know this stuff, by the way? Because if you know it, I can, did you do it in physics? No? Yes? Okay. So, very briefly. Then, if you remember, you have the radiant flux. I see faces. Not everybody did it, right? I have a right impression? You have something which is called the radiant flux. What is the radiant flux? Is the rate at which energy is flowing in or out, well, it depends from the sign of the flux, okay, over the unit of time. This is the radiant flux. The radiant flux is also called radiant power and is measured in watts. Okay. If you want to calculate the illumination on the surface of a scene, what you need to know is the radiant flux per unit area outgoing from a surface. So the outgoing radiant flux per unit surface is what we call is our base for calculating the illumination. And this is what is called radiosity. Radiosity is watt on a square meter. That is the radiant flux over the unit of surface. So B, radiosity, flux over surface. The value I, which is the one I'm used to use as well the output of our Funk model. When we are fiddling around with the Funk model, the result is always I. And then you remember that we convert I to a quantization step in the RGB 24-bit frame buffer, right? We get I from the Fog model, then we apply the logarithm in 256 steps for each channel to calculate over which quantization step we can represent that kind of intensity. To get to that intensity, this is not the radiosity per se, but I have to relate the radiant flux in a specific direction per solid angle unit per area unit. Or more often, simply, I have to specify just one direction in which I am considering the radiant flux. Because the problem of the flux is that I give the time, I give the surface, but I am not giving any direction. So by convention, I will define the light intensity as the radiosity, which is outgoing from the surface, in the orthogonal direction, which is just only one of the infinite possible directions in which the flux can be outgoing. When you're using a ray-based model, I've boiled this down very to the basics, and even so it's boring. Imagine with the full gory details. because just this slide, it's just, oh, okay. But actually, if you could go in, then it would be another 30 slides. Those I'm sparing you. So, okay, in ray-based models, light sources are considered separately from the surfaces in the scene. If you're using radiosity, each surface is an emitter. So actually, the idea of there is a light source and there is a surface which receives the light source, actually that idea is sort of thrown away in radiosity. In radiosity, every patch is an emitter and every patch is an absorber. You don't have any specific distinction between the light source and an object. The only way in which you can really tell which is a light source and which is not is that probably the radiosity from the light source is outgoing, in outgoing direction, is much more than the radiosity of a patch, which is basically absorbing. The whole environment is divided into n patches, each one of finite dimension, which emit and reflect uniformly across their entire area. So each patch has the same, is supposed to have the same radiosity. For each patch in the balance, it is necessary to consider the incoming energy from other surrounding patches and the energy which is emitted by each patch. So you do the balance, what I give and what I take. The whole patch system can be therefore represented as a set of linear equations. So the total, well, the radiosity for each patch. So patch number I is given by the outgoing energy, so the self-emission of each patch. This is very high in light sources. Well, in a patch which belongs to a light source, it could be nil in a patch which is not emitting anything because it's not a light source. Through a set of different things over here, but basically plus the incoming energy from other patches. So the radiosity, the energy per time, per surface is given by the energy I create from myself, because, for example, I am a lamp emitting with incandescence, plus the energy that I receive from the others. Like, for example, I don't know if you can, probably not, but if you are standing somewhere on this floor, you can look at this patch. You see that this patch, so it's emitting, but it's not emitting because of self-emission. It's emitting, so its EI will be 0, but its BJ, or its sum of BJs, is such that it gives me a positive radiosity. That is a reflection. So this is the basic idea, right? You with me, or you're against me? You with me, right? More or less. But of course, the nature of this BJ has to be somehow corrected, adjusted, according to a number of considerations. These are the considerations over here. Let's look at it more in detail. You have to give to the patch what it is basically an absorption coefficient. This depends on the material. So there will be material which reflects less. There will be materials which reflect more. This is expressed with the reflectivity factor for each patch. This is usually attached to the material of which the patch is made. In 3D models, usually you assign to a mesh a material. This material brings a series of parameters. One of these parameters is its reflectivity. So when you very easily with drag and drop or with the menus, you can say this is made of glass, this is made of metal, this is made of wood, this is made of stone. This is assigning the material to a surface. This is specifying its reflectivity. Fj is something which is called the form factor. The form factor is a coefficient which gives you a weight, and this weight makes bigger or makes smaller the importance of the radiosity of patch number j. What do I mean? In order to have reflection over here, this patch up here from the floor, from the lamp, is very important. Why? Because it's right on the top of the tile, and they are exactly one parallel to the other. This is the best possible situation to transfer energy from one patch to the other. So its form factor is near 1. It's the maximum that you can have, 1. Like, for example, when you put your hand right on top of a candle, then you are experiencing a form factor of 1, which is actually, ouch, it burns. Why? Because you have the best possible radiosity factor configuration for transferring energy from the patch of the flame on top of the candle to the back of your hand. But if you move your hand not on the top of the candle, but right on the side of it, what happens? Well, nothing, the flame doesn't change. It emits the same quantity of energy. And your hand didn't change. It still has 5 fingers. But what's changed? The geometry of the problem changed. Your form factor has turned 0, because you are in the worst possible condition to obtain energy from that specific patch. You see? This is the same thing that the form factor tries to model. You go to 1, for this patch over here has a lot of contribution, so this Bj is transferring completely, well, of course, modulated by reflectivity over here, because there will be an absorption given that the material. But for example, that other patch over here will have an influence, because I can make a coupling between that patch and this patch, but the form factor is completely different, because I don't have a face-to-face situation, but I have an inclined geometry. So the influence of the radiosity outcoming from that other patch is much less than the influence of this patch over here. This is called the form factor, which is over here. We will see it. And the other thing is the ratio of the two areas of the patch I am considering. If I'm considering a big patch over a smaller patch, then this has an effect of a multiplier, because it's a big patch with a lot of energy over a small patch, or the contrary. We need to determine the quantity outgoing from the entire Ij, which has an impact on an area unit of Ai. Therefore, you need to scale them down in this way. You have to consider with the effect that the different sizes of the patch have when you're using patches of a different size. You need a break? Go. This is the problem of the form factor, you see? If this patch, which is patch I, is receiving from patch J, the radiosity which is coming out from patch J will not fully transfer to patch I. Why? Because the form factor is different from 1. The form factor depends from the mutual inclination of the patches, and from the distance, and from the area of the emitting patch, and from a switch, which is called H. This switch is 1 if Aj is visible from Ai, and it switches everything off to 0 if there is an occlusion between Ai and Aj. Okay? Because in computing the form factor, you should also check, when you're picking two pairs in your algorithm, if there is something in between which covers completely patch A from patch J. If there is, then you do not have any radiosity transfer between the two patches, and you will put H to 0. Putting H to 0 puts the form factor of the problem to 0 over here, which in fact has the effect of completely taking away the radiosity contribution of that patch on the patch that you are considering. You see how it works? Huh? Sharon. Stone. Yeah, shadow. Oh, okay. I understood Sharon. Sharon Stone. Which is okay. I mean, she's kind of an old goose now, but still viable. One of the most intelligent women in the show business. QI out of the top. Okay, so imagine that we have managed to divide everything in patch, balance everything, and using these ideas over here, we have a value of B for each patch. So if I have divided everything into 2 millions of patches, I have a value of B for each patch, from patch 0 to patch 2 million. What do I do with these B values? I have to convert them into intensity values. So for each B value of each patch, I told you, but by convention, I have the problem that I should take into consideration the direction of the flux. Because I define the flux over the unit of time and over the unit of area, but I'm not telling nothing about the direction in which the energy is emitting. So I am, by convention, considering everything like in the candle. That is, the radiosity is coming out orthogonal. Okay? That is why when you put the hand on the top of your candle, you get burned. Okay? Because you are considering the radiosity, the direction, well, actually, the radiosity direction is like this, coming out orthogonally. So basically, to express the direction using steradians, which is an angle, a solid angle in all 3D direction, you can model complete orthogonality by putting delta omega cosine of phi to Greek pi. So you just divide everything by Greek pi. It's not apple pie, but Greek pi. And dividing everything by Greek pi, you convert your radiosity value to something that we call the intensity. I have a surprise. This B value, this theory of the B value, is okay if we consider a monochrome light source. But light sources, in general, in reality, are monochrome? No. So what do we have to do? To make this mess for every channel. So calculate the radiosity of 2 million patches, considering the red component of the light sources. Calculate the radiosity balance of 2 million patches for the green channel, calculate the radiosity for the blue channel. So it's 6 million calculation. Then use everything to calculate the intensities. So derive the intensity of the red channel for patch I from the value of radiosity for the red channel for patch I. So you have to make 3 calculations of radiosity for each patch. Radiosity comes from all possible combination of all the patches. Therefore, you might understand that the more the patches, the more the mess. Okay. So, one big advantage of radiosity is that it accurately gives you a physically based result. So it is much more realistic than ray tracing. The other side of the coin is that it is very heavy computationally. If you want to try performing a radiosity rendering, you might try using POV ray. You know POV ray? POV ray, persistence of vision ray. In POV ray, no, this is ray trace actually. In POV ray, this is a result of a ray trace. I don't have the radiosity result. But it's very interesting because with POV ray you can upload your 3D models and you can very easily specify to render them in radiosity or in ray trace. And you can compare the results. So if you want, if you have time, you want to fiddle around, you can download for free POV ray and you just look into the online help how you can configure the renders. Everything is script-based, so there is a language. We will see a little bit of POV ray in the next semester, but not now. And you can experiment a little bit just to see how the same thing can look differently using the two different way of renderings. Or if, for example, you have a demo version or a demo version which is not time limited, for any kind of reason that you might be able to obtain such a thing, you can set up in Max 3D very easily also in the rendering parameters that you want to use radiosity. Max automatically divides your model in patches, and you can perform a ray trace rendering. Here I made two renders of the same model, which is the inside of a library. Here I used ray tracing, and here I used radiosity. The problem here with ray tracing is that I had just the light sources over here. I had 4 light sources like this. And in ray tracing, these were not enough to properly create illumination of the environment. Actually, on the screen, it looks much better. It's the problem of the projector here. You don't have enough contrast. So all the shadows here are kind of messed up. But if you see it, if you go on the slides, not on print, and you look it on the monitor, you see that there are things over here. Just the quality is not very nice. But you already see that the appearance is kind of crisp and shine. This is the same thing in radiosity. The appearance, well, the lighting here is correct. Well, that was because the lights were disposed and placed having radiosity in mind more than ray tracing actually. But you really see that you have a much softer, much diffuse appearance. And here is to make you see something that actually through the beamer you don't see. But if you go on your PDF with your computer, you will see that you have light flooding and distributing outside the window, which is something with the ray trace you cannot do, because it really models the fact that energy is diffusing around and even diffusing on the courtyard at the side, and you have really an environmental lighting effect, very nice, very realistic, which is something which is rather hard to get in ray tracing. Okay, this is another thing you don't see with the beamer, but you will see on your slide. This is the model with a camera which is placed outside. So that's it. As you can understand, I just gave you a basic hint of the thing. I was rather quick intentionally because now I want to make a 600 seconds break. And after the break, we will open up an example of the exam, and we will take the last half hour to go through the exam and explain, try to make it together like an exercise. Okay? Okay, till the next. Yes?
12 secondi di video del progetto che stiamo facendo.
Sì, aspetta che mi sono appena chiuso fuori dal PC, ecco. Okay.
Stiamo facendo con la Clarissa, è lei che ci ha detto di fare... Lei ci aveva detto di rivolgersi alla Clarissa per fare questo rendering della cucina col video.
Ok.
Per ora ho renderizzato 12 secondi, ci ho messo tipo 12 ore per fare il rendering. Proprio che ho messo così alla buona dentro qua. Qui la qualità l'ho passata un po', bisogna scegliere. Si chiama 00300 001 Ho passato la qualità per... no, qui ancora 80, no, qui ancora a piena qualità, però l'ho fatta al 50% da Blender, non al 100%, perché ho visto il tempo che ci metteva e siccome era una semiprova. È un po' scuro all'inizio perché dopo ci sarà che si accendono le luci. Ecco, una volta giunto qui si dovrebbe accendere la luce.
Bello.
Ecco, c'è anche il lavandino così di là, qui non si coglie. Una volta accesa la luce, l'idea è, qua si accende la luce, guarderà la luce che è accesa, gira dietro, arriva al forno, punta verso il forno, si accende il forno, si rimette nell'angolo di lì, fa ancora una panoramica, così si vede anche il lavandino, la lavastoviglie, volendo si può fare accendere anche la lavastoviglie, basta metto un LED luminoso e lo faccio accendere, e poi basta, vado verso l'uscita.
Va bene.
Può andare come...
Ok.
Stiamo facendo anche la relazione con più o meno tutti i vari passaggi. Ok, io.
Ok.
Respiro sollevato.
Ciao. Questa è la vostra parola d'ordine. Come siete messi?
Adesso le facciamo vedere. Guardiamo dentro le case se sono tanti.
Ah, bene. Ci avete qualcosa da farmi vedere?
Sì.
Devo caricarlo qui o...
No, carichiamo.
No, appoggiati qua. Hey, Boiana, you're alive. Ok.
Negli edifici con la testa non si rispetta la boundary proprio.
Ma solo la testa, la gamba non ti riesce a far entrare. Cioè c'entri con la testa. Beh, ma perché il motore non è molto preciso, tutto lì. Bisognerebbe allargare, trovare dove fa la collision detection allargare la bounding box degli oggetti o dell'avatar, allarga la bounding box dell'avatar. Prova a sentire. Questo cos'è? C'è il tombino che
esce.
Ok. Quindi diciamo che avete fatto l'ambiente. Ma si può entrare negli edifici poi? No.
Potrebbe essere il default. No, l'interazione con i personaggi saranno al di fuori degli edifici. Nel garage si può entrare, per entrare negli edifici si devono scomporre comunque. Questo qua, il garage, ed è stato realizzato tramite 1, 2, 3, 4 pezzi. Sono 4 blocchi. Perché altrimenti
Sali anche sull'altro.
questa qua è soltanto per verificare per noi, vedere come l'attivazione. Che eliminerà.
Va bene. Adesso il prossimo passo qual è?
Dialoghi dei fare tutti i personaggi, i modelli rendiamo, testurizziamo i personaggi, li mettiamo dentro e dobbiamo associare i dialoghi, dobbiamo scrivere ancora i dialoghi dei personaggi. Stiamo formalizzando il processo, il tratto.
Senti, la navigazione avviene solo tramite i tasti cursore? E il mouse come funziona? Ah, ok, è così.
E poi il puntino lì in mezzo è quello che poi va a cliccare.
Sì, sì, sì.
C'è da dire che siamo dovuti stare molto bassi con
Sì, sì, vabbè, certo, se no non fa più niente. Certo, con la texture sopra. Vabbè, poi il problema della navigazione ci arriveremo. Va bene, dai. Andate avanti. Ok? Quando ci vediamo la prossima volta. Va giù, va luglio, giugno, va al secondo semestre. No, non posso. Cioè, non è che non voglio, che non posso proprio. Vabbè, tanto. Ok? Va bene. Sì, sono curioso di vedere quando parlano. E fate anche qualche oggetto che si mischia, Cioè, ok. Ecco, una cosa che volevo dire se riuscite a fare, perché il framework, così come adesso, scrive qua sotto, abbastanza piccolo, si legge male. Se si riesce a fare una cosa alternativa, o a fumetto, o a...
E lui aveva detto qualcosa che c'era un pezzo che si doveva cambiare
cambiare il render. Basterebbe, perché si legge male, o in alternativa o fare un po' più grande, l'optimum sarebbe fare un bel fumetto, cioè un ovale bianco con la scritta dentro sopra.
Sì, per i dialoghi.
Quando parla il personaggio, e quando rispondi tu, metterli magari sopra, cioè fare una cosa un po' più facile da capire.
Sì, gli aveva già chiesto anche, perché aveva chiesto banalmente per togliere il contatore di frame e per altre cose. Per voler mettere altre cose, guarda, se si può modificare, guardate.
Ok, va bene.
Sì, piega mezzo minuto a caricare. Qui, su questo mostro.
Vabbè. Mi potete mandare un Word? è un war, un jar, con tutto quello che mi serve che io clicco sul jar e lo faccio andare. Cioè una roba che io, cioè teoricamente è tutto in Java, no? Quindi dovrebbe compattarsi in un bel jar eseguibile, io ci faccio doppio clic, se ho dentro il Java dovrebbe partire. Se me lo fate così, provo anch'io sulla mia mostro qui.
Da ora o al termine?
Ma se ce l'hai già ora che me lo dai su una chiavetta meglio, se no quando poi, cioè adesso, stasera lo fai, domani mattina me lo metti su un sito o me lo mandi. Cioè mi va bene al punto in cui è adesso, giusto per vedere come gira. Ok? Va bene. Ok. Sì. You have to wait for other call dates. The next ones are in, let me see, probably it will be something like beginning of July and end of July. No, you only have to wait until July. Сколько лет? Уже, наверное, 7 или 8. Почему? Мне было надо какой-то софтвер кракировать, как сказать. А инструкции были только на русском. Так что, нужно, смотрю страницу, страница смотрит меня. И потом я начинаю заметить, что это не так трудно. Вещи понимаю, алфавит сразу понятно, как работает. Чего?
Алфавит другой, он же...
Алфавит, конечно, другой, а не так, это не китайский. Можно понимать. Да? Это очень просто, потому что буква А, буква Н, буква М. Потом читаешь кондиционер. Кондиционер, что кондиционер, все понятно. Пальто, пальто, ясно. Так, в принципе, не трудно. Трудно правильно говорить. Мне понравилось начинать заниматься. Поступил в школу русского языка. Да, поступил в школу тут в Милане. Тут в Милане есть школа русского языка. Всем нравится. Почти каждый день я слушаю на улице, русские говорят. Полно вообще русских. Да, в Италии полно. Особенно в Милане, где делают шопинг. Целые команды женщин идут купить вещи. Ладно, давай. Dai ragazzi! Ciao. A lezione non venite più? Non avete già fatto voi l'esame?
Abbiamo un esame
Del sangue? No? Di pozzi? No. palle. Vabbè, facciamo così. Cattedra. Ma non c'è il mouse. Che palle. È bloccato, non riesco a aprirlo. Okay. Actually, I have one example with solutions, but it's on the network, and I cannot get to the network because the panel here is stuck, and I couldn't open it. So I have no network, no access to the site. Do you, maybe if you can access with the wireless? Ma il PC c'ha la tastiera e il mouse che sono nel pannello di destra che è bloccato, non si apre. Ci vuole il piede di porco per aprirlo. Forse ce la faccio con la wireless. Non ce l'ho. Ci deve essere... è questa qui che non si apre. Si vede che l'ultima volta che è stato chiuso c'è rimasto chiuso dentro qualche cosa e non... Esatto, cioè, ma o mi collego in rete o prendo la tastiera del PC. Quella l'ho aperta a fatica, ma questa no, perché qualcuno si vede che quando l'ha chiusa, c'è chiuso dentro qualcos'altro in mezzo. Ho sbatacchiato un bel po', ma... Secondo me da sotto non si riesce ad arrivare, guardate cosa c'è dentro da sotto, perché c'è qualcosa che è tipo un cavo, c'è un cavo che è rimasto impigliato qua in mezzo. Hai visto? Ecco, perfetto. Cos'era? Ah, la tastiera, cazzo. Ah, infatti è partito un tasto. No. Vediamo se parte, giusto per scrupolo. Vabbè, ma è già acceso. Allora. Provo un po'. Funziona, sì. Che adesso c'ho la rete. So you can go. Sì, perché mi serviva la rete o la tastiera, ma erano tutte e due dentro la... Basically what you have to do is you go to the course online web page. Okay. This is the forum, you see? You have many questions, and you just, even if some of these start in Italian, I believe that some student, yes, some very helpful student translated the questions that were put into Italian. So everybody can understand the questions and the answers. So it's nice even only to go through the forum and look for the questions and the answers. And so that's one thing you can do. It's written here, you see, many facts and answers are in the forum. here you have theory exercises with solutions. Here you have to download and practice on it carefully. So I'm getting now. We will open it up and see what's there. Okay. You see there are 8 basic exercises you should be comfortable with. I'm afraid that they are in Italian. Let's see. Yeah. Yeah. Yes, this is eigenvalue. This is, for example, an exercise that gives you. These are 3 eigenvalues. From these eigenvalues, I already provide for you these eigenvectors. And this eigenvector is coming from the first element of the vector of the eigenvalues. Then I give you some points belonging to the polygonal mesh. Point 1, point 2, point 3, point 4. You have to calculate the 2 planes which are at the extremes of the main natural axis, which is R, of the bounding box, which is bounding the vertices, in a way that their covariance matrix is diagonalizable using the diagonalization matrix made by the given eigenvectors. You remember the theory? So you have to choose which is the correct eigenvector for R, and then calculate the planes. It's very easy. This is the formula, R minus mean and minus R max. You remember, those are the formulas of the 2 planes. So not a big problem about that. Let's see another one. There is Phong attenuation. Oh, this we saw already. Do you remember? We spent an hour doing an exercise which was similar to this one. You have the matrix, emissive matrix of a source, the absorption factors, PQR are 3 vertices of a polygon, S is the position of the source, COP is the position of the viewer. What I asked to you is to calculate the intensity of the color in vertex P. So what you have to do is basically calculate the 4 main Phong vectors. So you calculate the normal, you factorize the normal. You calculate the viewer, you factorize the viewer. You calculate the direction of the light source, you factorize the direction of the light source. You calculate the reflection, you factorize the reflection. Then you have to calculate the distance between the source and the point. Write the attenuation polynomial, and then calculate the contribution of the diffuse on the green channel, because it turns out that this light is only a green one. Over here, you see, there is only green. There is a part of diffuse green and a part of specular green. So you calculate the contribution to intensity of the green for the diffuse part. And there is the formula that you need to know, because it's from the Phong model. Then there is the contribution from the specular part. You sum the 2 contributions. And then you quantize it to 255 bits. But those you have in English in the slides, so you could follow that one. Then I think I have in English. I have them in English also. Let's see. Here I have a collision between a sphere and a plane. Given a wall with an energy field in a teleporter in an action video game, with a normal n, over which you have a point p with 0. Consider a spaceship with a sphere bound in volume of radius r, with center in q in the time t0 equals to 0. The velocity vector of the spaceship is such that at instant t1 equals to 1, the center of the volume of the spaceship would be in r. Determine if between t0 and t1 the spaceship can go through the teleport wall, and in which point. So I give you the normal to the energy field, the initial position of the spaceship, no, this is the P0, is the point on the teleport wall. Q is the initial position of the center of the sphere which is surrounding the spaceship. R is the position of the center of the spaceship at time 1. What you have to do is to write the equation of the plane over here, n0, n1, n2, and d, where d is minus n scalar P0, so this is the equation of the plane. Then you have to calculate the velocity vector of the bounding sphere, which is the difference between the 2 points that I've given you in time equals to 0 and time equals to 1. So this is the velocity vector. Therefore, you can write the motion linear equation, because you have the center and the velocity vector. And to verify if a collision is possible, you shift the plane of the same distance of the radius, which is 1. So this is the shifted plane of the same quantity of the radius. And then, of course, if the scalar product between the motion equation and the plane equals to 0 in some time, it means that in that time you have the collision, because the center of the sphere, of the bounding sphere, belongs to the plane. If you solve taking out the parameter t, which is the time, you have the usual equation which is intersecting the motion equation with the plane. It turns out that the time for which you have an intersection is 0.3, which is a valid time because it's a time between 0 and 1. Therefore, the center of the sphere at the time of collision is at these coordinates, 2, 2, 0.31. This, of course, is not the point of collision of the sphere. This is the position of the center of the sphere at the time of collision. To find the point of collision, you have to start from the center of the sphere at the time of collision and go down along the normal of the same quantity of the radius. And this gives you the coordinates of the center of collision at the time of collision, which solves the problem. So they will be more or less exercises like this. Nothing that we didn't do in theory, and this one is calculate the effective radius of a box whose sides are described by these vectors, r, s, and t, according to a plane with a unit normal direction. So this is very easy. This is the normal. You have to factorize the normal. Then you apply the definition of the effective radius, and this is the effective radius. So very easy. You can either use your pocket calculator if you want, or if you don't want to use the pocket calculator, you can work with factors. It's also possible in your working them out with your head. Head. So these are basic exercises to try. Then you have examples of exercises that you might find at the exam. Like, for example, this is an example of an exam. First exercise. You can download this from the web page. You are required to draw a computer graphics program which performs the animation of an object. The object is drawn by the function drawObject. Question number 1. Write the code necessary to set up the program. Open a window, set a perspective projection, declaring a callback which handles resizing of the window. So you will have here to do all the preparatory necessary code. So set projection to ortho or perspective, set the camera, set the viewer, the usual thing that you did in the laboratory. Draw the object and wait for user interaction with the keyboard. This is, of course, means setting up the idle callback, in which idle and the repaint callback. In the repaint callback and in the idle callback, you just write drawObject, which is the function which draws the object, and that's it basically. You have to show that you understood that you can do this by simply putting this in the idle callback. And then you need a callback for the keyboard. This callback for the keyboard will handle the key press. You did these things, right? Yes. And when you press this key, you translate, then rotate, then scale the object. This is a trick because you have to perform the necessary OpenGL calls in the correct order. Then declare the viewer and at least one light source. So you have at least, of course, you don't need to do this precisely, but you need to remember more or less how to organize the code. So it doesn't matter that, for example, to declare the viewer, you use GL look at. GL look at has, I think, 8 or 9 parameters. It's not important that you understand or remember, well, understand, yes, but remember the exact order of the parameters. Okay, you can just write GL look at, coordinates of the viewer, coordinates of the looked point, up vector of the camera, for example. So you remember more or less what you need. Yes? GLU and GLUT, yes. Yes. Here the focus of the exercise is to show that you know that OpenGL works with callbacks. So you need to show me that you can set up the necessary callbacks and declare them in the main loop. That's it. If you don't know what callbacks are, of course you are not replying or writing the solution to this. I mean, it's not since it's an exercise on paper. No, it's not something you can compile. The question is not that the code is extremely precise and compilable. The question is whether you are a general idea on how to organize your code. That's basically it. I'm looking for concepts, basically. This is an exercise. Consider a B-spline curve of degree 4, defined by 13 control points and 18 knots. These 18 knots are all simple and define a clamped curve. Control point P6 is at these coordinates, and it is first rotated of theta pi and a half, then translated with the following matrices. So this is the rotation matrix, and this is the translation matrix that you apply to the control point number 6. Question number 1. Write a B-spline defining relation for determining the values n, p, and m. So here you have to remember how many, if you have a degree number 4, what is the value of the number of control points and the number of knots? There is a relationship that you have to know. Then you have to cite which are the basis functions that are affected when you change P6, and which spans of the curve will change. This is the exercise that you had with a pencil on it. You remember? There was a B-spline, then there was exactly the same as exercise. Well, probably the span was changed or something like that. But the idea is, if I'm moving this control point, since you know the degree, you have to know which are the parts of the control of the curve which will change because of the movement of the control point, and which will remain fixed. So to know this answer, it means that you have studied that specific slide, which is giving you an example of this question. Then you have to compute the combined rototranslation matrix and explain the order of multiplication you have chosen. Because then you have to, in number 4, you have to transform P6. To transform P6, you have to multiply the coordinate of P6 with the rototranslation matrix. But first you have to compute the rototranslation matrix. So here you have to compute either R multiplied by T or T multiplied by R. Which one is the correct one? It depends from the sequence of the transformation you want to make. After you have computed the rototranslation matrix, you use it to calculate the new coordinates. And you give the new coordinates of P6 after rototranslation. So you see that in general, every exercise is made up of a very small task. So they are very small steps. So you just start from the first step and answer the very small question with a very small answer. And it's already 2 points. Then you go ahead, number 2. You answer it. It's already another 2 points. And you go on like this. It's very important for me that you put the corresponding number before each answer. Okay? So I don't want anything written like you want. You have to write 2.1. The answer is finished. 2.2. The answer is not write everything in a mixed order and then I have to find which the answer is in all the mess that you have written. Okay? I want a clear definition of what is your solution. Okay, 3. This is the difficult question of theory. So this is the question about OpenGL. This is the question about the geometrical computation. Then there is theory difficult, and then there is theory easy to save your ass. Theory difficult. Visibility determination is one of the key functions of a computer graphics engine. This is a sentence just to warm you up. Question number 1. Explain briefly how visibility determination can be implemented at polygon level, mesh level, and scene level, respectively. Polygon level, you remember that we have seen, you remember that day in September? We did something like clipping, you remember? So what was clipping about? We really clipped sides of the triangles because we were making, we clipped lines. So that's visibility determination at polygon level, very fine. At mesh level is bounding volumes because we group together entire meshes and we try to determine if these meshes are inside or outside the visibility volume. At scene level, you remember what we do at scene level? We use either octree, either binary space partitioning, which are 2 techniques to subdivide the space roughly and decide quickly if entire groups of objects, entire parts of the scene are altogether visible or not. This is actually explained in one slide where there is exactly a small commentary on the fact that there are different levels of visibility in which you can check, and really gives you the answer of this one. So if you remember that slide, it's easy to answer to this one. Then a little bit more difficult. Explain the basic principle of the Cohen-Sutherland clipping method in 2D. You remember Cohen-Sutherland? It was about dividing the clipping space in 3 by 3, so in 9 regions, and assigning outcodes to each region, and then assigning outcodes to every endpoint of each segment, and then confronting bit by bit the outcodes of the two endpoints. If there were some conditions, then you could make some conclusions. Which are those conditions? Which are those conclusions? Then there is Lion-Barsky. Why Lion-Barsky can be considered better over Cohen-Sutherland? So why is it better, and how is it structured to be better? Then, if you go to here, this is usually to get 30L, 30 lode, because it's the two additional points. Explain in a detailed way the Lion-Barsky method in 2D using an example and a drawing. Do you remember? So the alpha in, alpha out, alpha 1, alpha 2, alpha 3, alpha 4. So there is a whole method beneath. If you remember it because you have studied it, then you can gain 2 more points by showing that you know even how Lion-Barsky works. Then there is the theory easy question. Collision detection is one of the most fundamental techniques for 3D engines for video games. Number 1, explain how it is possible to test the collision of a sphere against a plane and write the necessary equation. Okay, that's very easy. Number 2, explain how it is possible to determine right away that a collision against a plane will not occur without solving the intersection. This is easy. You just consider the velocity vector and you perform a scalar product with the normal. If it turns out that the normal and the velocity vector are orthogonal, it means that the plane is parallel to the direction of movement of the sphere. Therefore, they will never intersect. Therefore, it will never be collision. So, even something like this, very easy, it's okay, 2 points. Number 3, explain how it is possible to compute the coordinate of the point on the sphere in which collision occurs. Write the necessary equation. Once you know the center of the sphere, since you know the normal to the plane, you go down by the normal of the same quantity of the radius. So, the coordinate of the sphere is the center minus r, scalar the normal, and you go down to the collision point. You may do a drawing, you may write the equation, and that's it. Number 4, explain how to test the collision of a bounding box against a plane. Write the necessary equation. It's like with the sphere, but you have to bring in the concept of efficient radius. Then you have to write the equation of the efficient radius to show how efficient radius work, and that's it. I mean, it's feasible if you study it. There are no surprises. It's everything and only what we have been talking about during the course. I think it's very honest in this regard. So this is okay. You have several of them. You can go around to all the different, but you will see that there are slight variation of these themes. Let's see if I have something else that I can show you. I think this is about one. No, this is an entirely different example. Oh, this is so boring. Fong again. Fong and Fong, always Fong. So as you can understand, Fong is much, because it's rather mechanical, so everybody knows it, so it's safe to use it in an exam. Let's see this one. again. This is Fong, but there is a small variation. This is an example of the variation you might expect. In the exercise, you add Fong, normal Fong with a point source. So this one looks the same, but if you have studied by heart, so you just don't read the text, you miss that the light source is a spotlight and not a point light, and that I give you the direction and the conic distribution factor. This, of course, changes a little bit the exercise, because your equation has to take into account that you don't have a spotlight, point light anymore, but you have a spotlight. So everything will have to be multiplied at the numerator for u by the direction in which is pointing the light, L, and everything has to be to the power of beta, which is the conic distribution factor, and then the rest is the same, basically. Here there is another difference. You remember the one we saw earlier. The one we saw earlier, it was only green diffuse and green specular. Here you also have red diffuse. So there will be one equation more to calculate. So if you have understood the method and you are careful in looking at the text, there is nothing conceptually more difficult than this. You have to acknowledge the variation against the base exercise and behave accordingly. This is the canonical question about global rendering. This is the easy question, save your ask question. Global rendering is a fundamental process for the synthesis of computer images in computer graphics. Explain the difference between a global and local illumination model. This is something that we have been talking today, remember? Explain in which way the font illumination model and the ray tracing rendering approach are related. Also, we have been talking about this one. There are slides about this thing. Explain what is radiosity and what are benefits and disadvantages in relation to ray tracing. So the ability to rendering diffuse materials, the fact that in ray tracing diffuse material tend to make the ray tree explode. Okay, so these things, we have been talking about them. Explain the physical and mathematical relation used in computer graphics between radiosity and illumination. We have seen this today also, so the relation between energy, color, the Planck equation, what is radiosity, so the flux, etc., and how it relates to illumination, the fact that we have to, by convention, decide the direction of radiosity, so that is why we divide by pi, etc., etc., etc. So those slides over there. There are a little bit more complicated questions. This one is about Bezier curves. Explain why Bezier curves are very interesting, are a breakthrough, a revolution in computer-based design. That's because it's the first time in the history of computer graphics that you can draw a curve without knowing its equation. You just use a set of control points that give you an axis which is very user-friendly and has a very defined geometrical meaning. And you can basically design the curve that you want by just moving the points. So it gives you, there's a slide that talks about friendliness, easiness of computation, etc., etc., etc. Then a little bit harder, what are the working principles of a Bezier curve, so why the Bezier curve works. Here you have to talk about the Bernstein polynomials, the partition of unity, the fact that basically the equation of a Bezier curve is laying down a set of weights. So the coordinates of the curve is the result of setting a continuous relationship weight organized around the Bernstein polynomials, which make a partition of unity. So there is a theory that we have been explaining with examples. Then you make a step ahead to B-splines. What it is that you cannot do with Bezier curves. So you have problems if you want to do complex Bezier curve and make them compound. You're starting losing control. So instead of making more than one Bezier curve and compound them, you use B-splines, dividing them into knot regions. So B-splines add the concept of knots, how they work, how they are defined. Yes, explain in detail the concept of knots and knot points, so why they are there. This also, there are several slides that explain this thing, and we have been explaining it during the lecture. Then you have to explain why B-splines guarantee a localized effect on the curve when you change the control point. We have seen that when you move a control point in a Bezier curve, the whole Bezier curve changes because of the Bernstein polynomial and the fact that the Bernstein polynomial is everywhere greater than 0. Whereas in the B-spline, you have the Knox-de Boer formula as a base parameter for weighting. The Knox-de Boer formula is a recursive definition, which is 0 everywhere except on expanding span around the control point that you are moving. So this gives you a localized effect. So you can more or less explain how the Knox-de Boer formula works and talk about its geometrical properties, which cause a localization in the movement of the points of the curve around the control point. So you can elaborate as much as you want on this. Well, that's, as you can see, there is nothing I didn't talk about during the lecture. And in any case, if you weren't at the lecture, there is nothing I said on the lecture which is not on the slides. So you can read on the slides. The problem is that sometimes it's hard to understand and fully assess the problem only by the slides. So of course, being at the lecture and having listened to the explanation, like it's supposed to be in every course, is supposed to be a great help. Okay, as always, I believe that there are no questions now, and I read some frustrated faces, but I believe that you should give you the possibility to study these things a little bit more in detail. So please study everything carefully one time, the first time. And you will see that there will be no problems with the exam. In any case, if you have questions, since we are not meeting anymore until the first call, you might ask questions through Messenger. The email is a little bit more difficult because I receive a lot of emails every day. So if you send me an email, you will get a very nice yellow flag on your email. It will go down in the queue of the flags. My backlog is around 80 or 90 messages. So it takes time to arrive answering to your email. So if I'm not answering, please do not send again the mail, because the effect is that I put another flag and it goes in the backlog together with your other mail. So keeping sending me an email does not speed up the process. It just makes my backlog bigger. Whereas in Messenger, if I have time and you have a quick question, you can type your question and I can type the quick answer and that's it. Questions like requiring me to write books in answer are less likely to get answered, of course. Make a quick question. Why the question is quick? Because you already studied everything and you already understood the basics. So you really have a very small detail that you want to get clarified. A typical example are in the forum. So in the forum, you find a lot of questions that have been properly answered. So usually most of the doubts get clarified from the frequently asked questions. Okay, thank you much for your attention. It's been a pleasure showing you the fundamentals of computer graphics. I hope that I have been showing you something which is interesting and that you might apply for your future career. And well, see you at the exam.